Hello. I hope that things today are not very quick. But please try to go to the links and the code in GitHub and try to practice. Run the code one more time and try to make some changes. Maybe also you will discover some problems, mistakes. But now we need to use autoencoder. We can use it for dimensionality reduction. So in dimensionality reduction, we try to reduce the dimension of input data from or input features. As this example, from 784 to 32, for example. But we can use also autoencoder for denoising. And this is very important. So we can, autoencoders are capable of learning new and improved representations from the original data, capturing the most important element. And regarding noise, disregarding the noise in the original data. So we can train a model with the input will be the image plus noise, and the output will be the original image. So we can train the autoencoder to remove noise from image. So some examples, imagine recording a conversation between two people, for example, at noisy coffee shop in the middle of the day, and we want to isolate the signal from the background. So in this case, the input to the autoencoder will be the signal plus background noise, and the output will be only the pure signal. So in this case, we will train the autoencoder to remove the background noise from the conversation. Another example, imagine that you have a data set and it has also some noise, blurring effect and so on, and we want to isolate the core image from the distortion. So in this case also we can use autoencoder. Imagine also that you are driving early morning and it's foggy. So we can use autoencoder also to try to remove, we train an autoencoder with fog and to train it to remove the fog effect from the images, for example. So it can give you better driving when it's foggy, for example. It's not a problem here maybe, but in some other places it's very, very dangerous. So we have this example from also MNIST dataset, but I don't have a dataset with noise. So in fact, I have MNIST data, and if you can see it here, I use the X-train and the X-test. I don't care about Y-train and Y-test because it's unsupervised. So when I uploaded my data, I uploaded X-train and the X-test. I divided each pixel value by 255 to normalize it. So now after dividing it by 255, each pixel value will be a number between 0 and 1, right? So now we don't need to normalize. So you can do normalization, or you can just divide by maximum value or by the range, in fact. So this is the range. I mean, in the function for normalization, we divide by range. We divide each value by range, and the range here would be the difference between minimum value, which is 0, and maximum value, which is 255. So the range is 255 minus 0, which is 255. In this function, in fact, I try to add some noise to each image. So I try to add Gaussian noise, for example, with mean equal 0 and variance equal 0.5. So I'm just adding some Gaussian noise to each. So this is the original image, and plus the noise, we can get this one. But it would be nice if you can work with maybe real data set. But just this is for demonstration. So now I have the input image will be this noisy images, this one. And I want to train the autoencoder to try to remove the noise from the image. So the autoencoder will be, the input to the autoencoder will be image, noisy image. And the output will be just the image, pure image or clean image. So when we train the autoencoder, in this case, it will try to remove noise from images. So how can we do it? I defined autoencoder, and it must be symmetric. So I selected here 4 layers. So we have 4 layers for the encoder. and the 2 layers for the decoder, right? I trained it for MNIST dataset, so the dimension of the input will be 784. The code size will be 120. It will be, I mean, the first layer, it will convert it from this size into 128. The second layer will reduce the dimension from 128 to 64. So this is the code size, right? This is the code. And the decoder, it will do the opposite. So it will convert 64 into 128. And from 128, it will be converted into 784. So this one, it's 4 layers, autoencoder, 4 layers autoencoder. So, and I did it also using Keras. So Keras is very easy to use, in fact. Very easy to use and very easy to understand and make some specific changes. I used here activation function, RALU, and in the output layer, I use the sigmoid.
I'm sorry, why is the input dimension for third layer 128?
This one? Yeah, because the autoencoder, we have 4 layers. So first, we will have this layer. This layer, the input will be 784, and it will generate 128. The second layer will be 128, and it will generate 64. And after that, the input will be 64. We will generate 128, and that's the end from 100.
So for layer 3, we have input dimensions as 128. Is that like just it should be 64 or?
Oh yeah. Sorry. This one. Yeah, this is correct.
Yeah.
This one should be 64. Yes, this one should be 64. Yeah, this is correct. So you will discover some mistakes, and maybe in the code as well. So maybe I need to go to the code and try to fix it. So this one will be 64. This is correct. So, and we will use this optimizer. We will use mini squared error, and I will train it for denoising. So now the autoencoder will try to predict the input will be noisy image. So it's X-test noisy, and this is the predicted image. I'm just using it for the test set. So the input will be this noisy image, and this is the output. So in fact, we can use autoencoder for denoising. I mean, some of you also are working with some data sets which has noise, for example. So maybe one idea is to try to remove noise using autoencoder.
Sorry, can I ask you a question about that?
Yes, please.
What if we use the labels too? Can you go to the last slide, please? No, maybe. When we put the data into the autoencoder for denoising.
Yeah. We just, it's exactly the same.
It's like we just upload X train and X test. So
yes, because we don't have labels. We don't need the labels, right? Because it's unsupervised. We are not using labels.
Unsupervised. So
yes.
If we use and we train both, it's because autoencoders in nature is some kind of supervised, but we fed them the X train at the first of at the input of the network and the output of the network, right?
Yes, we use the input as a target here.
Yeah. So what if we use the clean images at the output, and we use the noisy image at the input and the clean image at the output. So the network could learn the image better.
Yes, we did that here for denoising. So the input will be noisy image and the output will be the clean image. Right?
It's no. As target, we use again the noisy image. It's like
so you but in this case you train it to do what? Not to remove the noise, right? if you want to touch
No,
it to remove
I want
noise.
to remove the noise, but it's,
So if you want to touch it to remove the noise, I showed the input should be the noisy image, and I ask him, please convert this one into this clean image.
yeah, but we use the noisy image as a target.
In the output, no, it should be the clean image.
Can you go to the next slide? The slide that we are talking about is the.
No, I don't have the fit command
yeah, you
here.
don't have the maybe.
Yeah, but no, yeah, we will open it. Yeah. It's this one. Yeah, can you see my screen?
Yeah.
Okay, because also we need to fix. So this is we need. I mean, as you can see here, sequential and the model, we import it from keras.models. Should I make it larger? Can you see it better now?
Yeah, it's better.
Okay, so we have sequential, we have model, we import it from keras.models. We import also input and the dense layers from keras.layers. So this is very important. Those one. So from models, we import sequential and model. From layers, we import input and the dense. A plot model, we import it if you want to plot the model. So here we will, I don't know if, okay. Now I will load my data points and I will normalize it. This one is to normalize it because I know that the range of each pixel value is 255. And this one is just adding noise to the X test noisy now, it will be noise and the plotting. So I will just run that part. We can play with the mean and variance here. So now we have this is the clean image, and this is the noisy image, right? So now we will go for we define the autoencoder. This one, you are correct, this one is wrong. This one should be 64, right? Compile, we will. So 128 for 64, 128, 784. Now I will train it. Do you see? This is the command for training it. So the input will be the noisy image. Do you see?
But
and the output will be the train, the one which is clean.
So this is supervised learning for the noisy.
I mean, it's the same also for reduction, dimensionality reduction. It's supervised,
yeah.
But they call it. But they call it unsupervised.
But here it's supervised because we use labels. We know the actual image.
But here we use the input as the label, right? Not the label itself.
Yeah, but we have labels like. It's
yes. So now we will train it. I just fixed the validation set here because maybe it was better to use a GB or something. Maybe you can go back here to, now we are plotting. Here we are plotting. So, okay, we just need to wait for it. We will train it for 10 input. So the input here will be the noisy image. The output will be the clean image. The validation set will be, I'm using the test set for validation. And also the input and the output.
Yeah, I actually use the autoencoder for denoising my matrix model.
Okay.
It's it was underfitted, so I try to use a more advanced model.
No, you can go deeply. Try to make it more deep, for example, if it is underfitting.
I use also IRCNN, CNN, and they perform very they perform better than
yeah, if we look here for validation, it's training and validation, right? So this is a validation accuracy.
Um,
Look, it still goes up, validation accuracy. So I guess if we train the model for more time, it will the performance will be much better, right? So plotting those. So do you see? This is the performance even much better than. So this is the image plus noise, which is the input, and this is the output. Mm-hmm.
So if it is underfitted, we should add more layers, hidden layers to.
Yeah. I mean, if it is underfitting, try to make it more complex. So try to add more, maybe more hidden layers, for example, to make it more complex. Try to select different activation functions. Mm-hmm.
Thank you.
Can I ask one question?
Yes, please.
When you train this model, you used trained with noise and without noise.
Yes.
But can we, in practical implementation, we have like the training with input, which has a noise. But
Yes.
do we have also the input without a noise to train the model?
Yeah, because for example, if I want to build autoencoder to remove noise, so I need to have the same image with and without noise, right? For example, if I want to remove fog from the image, so I need to create a data which can help us to train the model. But for example, one suggestion, for example, so if I want to build a model to remove fog from images or smoke or whatever, so maybe I need to take the image one time when it's foggy, another time when it's clean, right? So when it's clear. So I'm just looking into the windows because sometimes it's very foggy and sometimes people cannot drive, for example. But I can take an image early morning when it's foggy, and I can collect the same set again, for example, when it's clean. So if you want to collect, if you can collect the data with and without noise, it will be very, very good. For example, light conditions. Sometimes in face recognition, we have a problem in light conditions. When it's dark, when it's illumination level and stuff like this, when it's sunny. So maybe you can take the same number of images at different times of the day, and you can train the model to remove those effects.
Okay, thank you.
So here in this example, I added the noise by myself, right? But maybe in reality, we don't need to do it. If you can take the images, if you can take pictures at different time of the day, for example, if you have a sensor and the sensor is working beside a machine and it's getting some noise from another machines, you can collect the clean noise one time, and after that you can switch other machines to have the noise effect on the measurements. So you can run the experiment in different conditions, one time to get the clean signal and one time to collect the signal with different types of noise. So
yeah, thank you.
Yes. So do you need anything in this code? Any question for this code? So at the end, we will just plot.
Sir, can I ask one small question?
Yes, please.
Can this kind of decoder can be used to remove errors or NaN values from a time series data?
But I guess in Python, for example, we have some functions which can help us because it's a data pre-processing, right?
Yeah.
If it is this NaN values, how can the model will be able to understand that we need anyway in pre-processing to remove those values or replace it with some numerical values for our model to be able to process. So it's a data pre-processing. So we need to fix those issues before training the model, because if you have NaN value, for example, right?
Yeah.
So how the model will explain it? Is it 0? Is it 1? Is it infinity? Is it?
Yeah.
So we need to replace it with some numerical values.
Yeah. Okay. I guess then simple pre-processing things can be used. Yeah.
I mean, autoencoder, it's useful if you are collecting data in a noisy environment, for example. Maybe you can remove noise.
Okay.
You are working with text and you have some problems in the text, too much noise. If it is speech, if it is images, video, So I guess it has lots of very good application. We are using it a lot, in fact, in this fault diagnosis and fault detection and
yeah, so this can be used in FDD, fault detection diagnostics.
Yes.
Okay. Yeah,
because usually we have some signals, and those signals, it has too much noise from the ambient noise and the other types of noise, and it's important to differentiate between outliers and the normal signal. So
yeah, I meant not just about the NaN values, but mostly about that kind of errors in the sensors. Sometimes sensors have a bias somehow. Maybe they get old or something like that. Or suddenly something knocks over, or it becomes 1,000 instead of 10. So something like that.
Yeah, I have two papers, in fact, with a student who was using those heavily a lot in
okay.
prognosis,
I'll write to you
diagnosis.
later about that.
Yeah.
Okay, maybe you can share that paper. I'll write to you later on.
Okay.
Perfect.
Yeah.
Thank you.
Okay. Thank you very much. So maybe we can go back to the slide if we still have something for today. It's just face recognition. If you want to do face recognition, it's the same. It's the same data set, in fact, but it's called the Olivetti faces. Olivetti faces, and it's each image, in fact, it's 64 times 64. So you can use this one for, you can use also maybe autoencoder for to compress those images to make it simple. I guess this data set, it's you can go to the, we have also the code here. So you can just go to the code. It's already there, in fact, the code. But if you want to try to solve it, build an autoencoder for compressing those faces, for example, it will be very, very good. But try to build your model and try to attach the encoder with your model. So this is very nice. Try to make it like this. So this is my model, which will make decision making, right? So after training your autoencoder, split it and try to attach the encoder layer in front of the model, because this one will do the pre-processing all time, correct? So after training it, just attach it to the model, freeze those weights, which means when you are training, because now the model will be a larger model, which composed of encoder plus other things, right? For those layers in the beginning, try to freeze weights so it cannot train again. And when you train the whole model, you will just train the weights which are here for in charge of decision making and the classifications and the regression and so on. So the model will look more beautiful, in fact, because it will be just one system. Because when we are working with principal component analysis, we need to do PCA for all data points at the beginning, and after that feed the data points or have this matrix. We have this matrix, so you need to keep this matrix with you all time. So to avoid this, you can just build the encoder, try to split the encoder layer, and try to attach it with new model, and retrain the whole model after freezing the weights of this encoder. Yeah, I guess this is all for today. So please, if you have any questions, just yes. Do you have any question for today? Supervised and super. I wish if we can have 1 week, in fact, for an example, maybe from reinforcement learning. But I don't know if any one of you has some experience in reinforcement learning. Maybe he can make maybe 1 hour, can explain the concept and make lecture, for example, in some simple examples. But I will try. I will try to make something by the end of the course about reinforcement learning, at least 1 week. It would be very nice if we can have some practical examples where we can try to test those RL. Maybe you can just select the most simple Q learning or something, most simple RL algorithms to solve very simple problem.
Can I ask a question, please?
Yes, please.
Yeah, so I have a model which is sequence to sequence decoder encoder based model for using LSTMs as encoder and decoder. And I have a list of parameters and list of inputs and list of outputs. And I want to use PCA to reduce those number of inputs. Is that possible?
But you have already the encoder, correct?
Yeah.
So the encoder already can be used for dimensionality reduction. So why do you need to use PCA at the same time?
Okay.
So you can, I mean, you can use autoencoder for dimensional, because PCA and autoencoders, you can do the same task. Because the problem,
Okay.
in fact, in principal component analysis, it's a statistical tool, right?
Yeah.
And maybe, I don't know, I didn't make any comparisons between autoencoder and principal component analysis in terms of outliers and stuff like this. But if you can have autoencoder already, which can be integrated into your model, it will be easy to integrate autoencoder in your model compared to principal component analysis. So maybe you can just stick to autoencoder and try to, but at the same time, you can make comparison. I mean, try BCA, and after that, to make some.
If you have a bit of time, maybe it will be a bit interesting. I can show you my model.
Okay.
The image, kind of image you showed before, LSTM image. With that, maybe you can see.
Yeah. Okay. So can you prepare something, for example, for next week? Maybe 20 minutes or something.
I have a whole paper presented. I can show the results and everything.
Okay. Yeah.
Yeah, maybe then we can do it next week. Yeah, we don't need to discuss now. It's not that.
Okay, but also you can share your screen now, because we have 9 minutes.
Yeah,
Yes.
yeah. So that's what I was doing, but I can't do that. Maybe I have to allow.
All people should be able to share, in fact.
It says host disabled participant screen sharing.
Okay. So what is your name, please?
Gaurav.
Okay. Yes.
Okay, can you see my screen?
Yes. Yes.
Yeah, so I have input layer which takes 54 outputs, 54 inputs for 720 time steps in the future, and it predicts in the end 216 it takes 720 in the back 54 inputs, and it predicts 216 time steps in the future and gives out 9 output. So my decoder LSTM has 100 cells, and then same encoder also has 100 cells. So is this already doing kind of dimensionality reduction in between, or?
So you have how many steps? You have 720 steps?
Yes, in the past.
Okay, and 54
inputs.
Inputs.
Yes.
And the output will be 100.
Output of the whole black box is 216 time steps in the future and 9 outputs.
Okay, but this one, it's predicting. No, maybe the one underneath it, it's 216 times 100. What does this mean? 216 times 100 is the number of steps.
100 is the number of cells for LSTM. 100 LSTMs.
Okay. Yeah. Now we are reducing. So okay. Because the input to the encoder was 720 times 54. 54, it's number of cells, correct?
A number of inputs for my data.
Number of features.
Number of features, yes, sorry.
Okay, and how many features from this decoder LSTM?
It's getting 9 out. In the decoder LSTM is same 100, but then this time distributed dense layer makes it 9. Well, maybe it's a bit confusing now, but I can make a presentation and show the results.
Okay, just to try to, present how do you organize your data? How?
Yeah, I'll show everything. I have already made a small paper, which shows some good results. I can show.
Oh, this is very good.
Show how it's working. Yeah, then I can do that next for the next.
This is very good. Congratulations! You are very. Did you start in this work from before the course or after?
No, this I sat in the last weekend, I think. This one was just showing for a small report. I had a virtual geometry and I was getting simulation data. I was not using real data. Because yeah, but I can make a presentation and I can show.
Okay, this is very good. Congratulations. Yeah.
Okay. I mean, this is not the final paper which I'll submit to you because this doesn't have any research objectives. Here I'm just discussing the results.
Okay.
So I want to put some research objectives and kind of mold it somehow.
Yeah. Okay. Yeah. Thank you very much.
Yeah. Okay. Then I can make something for next time.
Okay. Yeah, it would be very good. Yes. So thank you very much for today. Anyone else has any questions for today? Tariko, she has the size of the data to classify. It's a hyperparameter also, Tariko. So you need to decide it by yourself, or maybe you use grid search, for example, and you need to try different values. So, for example, I mean, she is asking about the code size. What is the optimum code size, for example? So, in fact, no one knows. So maybe you need to try it.
In a situation where you have to collect field data, then you have to decide, for example, how many days data that you have to take, or something like that. In that case, how you will know, like.
So do you talk about the code size or the data size?
No, the data size.
Of course,
Sorry
the data size.
Voice.
No, no problem. The data size, if you can collect more, it will be much better if you can, right? But because maybe it will be expensive to collect much data, so you can just go for cross validation if you have very small data set, and try to use also principal component analysis or autoencoder to reduce data dimensions, so you can build a simple model which can be trained using your small data set. So in fact, today, when we try to use principal component analysis or autoencoder, we use it because we need to reduce the dimension of the data. And then when we reduce the dimension of the data, we reduce the model size. And then when the model size is reduced, it will have less number of weights. So it will be easy to train it with the limited data set which we have.
Okay.
But if you are collecting data, try to collect as much as possible. Right?
Okay.
Because the data, this is a source of knowledge which we are used for training our model. So try to collect as much as possible if it is not very expensive. But of course, there are lots of limitations, maybe in time, economy, and maybe it's hard. So how to avoid those kind of problems? How can we deal with a small set of data set which we have? Use dimensionality reduction to reduce number of features. And then when we reduce number of features, the model will be simpler. So we can avoid overfitting stuff. When the model is simpler, also we can train it with less number of data points, because if you have 100 or 200, so I cannot have a model with 1 million weights, right?
Yeah.
Because it will be impossible to train it. At least we need to have maybe number of data points, maybe twice or 3 times number of weights which we have in our model, right?
Okay.
So if you don't have enough data, try to simplify your model using principal component analysis and autoencoder, and try to use cross validation, right? So we can get rid of this hold out validation stuff. Yeah.
Okay. Thanks.
Yes, thank you very much. So thank you very much for today, and have a great day, and see you next week.
Okay, see you. Bye.
Thank you.
Bye.
Bye.
Thank you very much. Bye. Thank you. Bye.